Okay, so far in the previous chapters, we've talked about differentiation. We've talked about how differentiation arrives from limits. Okay, from the limit definition, we've talked about the differentiation rules, and recently we've talked about the applications to curves. And now we're going to move on to applications of differentiation to other real-world situations. Okay. Specifically, some of the ones that we'll be talking about are kinematics. And kinematics is a branch of physics that relates to the motion of certain objects. Okay, and we'll be looking at simple versions of this. We'll be looking at motion along a straight line. Okay, and we'll talk about that in a little bit. We'll also be talking later on in this chapter about rates of change. Okay, instantaneous rates of change. Specifically to geometry problems, economics problems, maybe some engineering problems, and optimization as well. Okay, optimizing maybe trying to find the maximum of some point. When is it smart to find the minimum of some function? You know, you want to use the optimum situation to make a decision. Well, you can use differential calculus for that. And if you're in HL, we will also talk about related rates as well. Okay, but this will all be in another video. We'll just be in other videos. We'll be focusing mainly on kinematics for this series. Okay, so what is kinematics? Kinematics is the motion of particles or objects moving in a straight line. Okay, so you'll either have horizontal movement, so where a particle moves this way and back, and it can go in either way, right? Or you'll have it in a vertical situation where a particle could go up or down. Okay, and this will be the simplified version of kinematics that we'll be focusing on when we talk about differentiation. Okay, here are some key vocabulary words that you might want to write down. And these words will be going through one by one throughout this video. Kinematics, displacement, velocity, acceleration, initial conditions, and motion graph. Okay? If you have taken a physics course or are in a physics course, some of these words should be very, very familiar to you. Okay? You may not have learned it in the context of calculus, so if that's the case, then this will be another way for you to interpret some of the physics concepts that you've learned in those classes. All right, let's start with displacement. Displacement is basically if I have let's say point P, and it's moving along a straight line, okay, and to the right of P is the positive direction, and to the left of P, or to the left of O, sorry, I should say O is my origin, P is my point. If I'm to the right of O, okay, then it's a positive displacement, and if P is on the left side of O, it's a negative displacement. Okay, so what do I mean by displacement? Well, displacement really is just the position of P relative to O. Okay, it's how far he's gone from O, but it's also telling you the direction. Okay, so if he's on this side, he's positive S away from O. If he's on this side, he's negative S away. All right, so it's slightly different from distance. Distance is an absolute value; it's a scalar quantity, but S of t, displacement, is a vector quantity. Okay, and we touched on this briefly when we talked about vectors. S of t is a vector because it has a magnitude and a direction. Okay, and this is basically what we just talked about. If S of t is greater than 0, P is to the right of 0, or right of O. If S of t is 0, so if the displacement is 0, then that means P is right on top of O. Okay, right on the point O. And if S of t is less than 0, then P is to the left of 0. Okay, so just keep that in mind as we move on and talk about displacement and velocity and acceleration. All right, so to help you visualize what this means, we could have, we'll draw something called a motion graph. Okay, and this is a graph that describes the motion of P along the horizontal line or vertical line, depending on the situation. So let's say that S of t is t squared plus 2t minus 3, and the units are in centimeters. Okay, so right here I have, let's say right here I have the point 0. This is my origin. Okay, and P, the displacement of P is described by this function, where t is time. Okay, let's say t is in seconds. So the displacement of t, let's say P will follow this pattern always, right? Follow this function. So at the time 0, we can't have time as negative, right? So at time 0, if I plug in 0 here, okay, sorry, this is incorrect. Okay, this should be something else, but let's just assume that this is a function and this is what I get out. Okay. Well, if this is true, what I'll get is if s of 0 is negative 1, let's just say that. Okay, this function doesn't necessarily give me this information, but let's just say that it did. If I get s of 0, I would get, if I put in a 0 for time t, I get the displacement of negative 1, so that means I would be right here at the time 0. If 1 second passes and I get a 0 out, what I'll get is I'll be right at here. Okay, because the displacement is 0, I'll end up being on the origin. If after 2 seconds and I get 5 out, then that means my displacement at time equals 2 will be 5, so I'm over here. Okay. After 3 seconds, my displacement is 12, so I am all the way over here. Notice that this is not a linear pattern here, okay? Notice that something is happening here. You can see that the velocity is changing, and my acceleration is changing, okay? How fast the distance between this, after every second, the distance between each consecutive 2 points, right, is increasing, which means my velocity is increasing as I move on. So some observations you could make here is that the displacement function does not necessarily have to be a linear function. Okay, it could be moving randomly depending on how this, whatever the function is. Okay. So that's called a motion graph. Let's talk about velocity. What is velocity? Velocity from science class is the average, well, there's 2 types. One is average rate of change. Okay, one is average velocity and one is instantaneous velocity. Well, since we've been talking about secant lines and tangent lines, I think you have a good idea of what this means. Average velocity is just like the average rate of change on a graph. Okay, if I had the distance between 2 points, it's an approximation of how fast something is moving. So the average rate of change between these 2 points is the slope of the secant line, and so when we talk about velocity, if this was s of t, okay, the velocity would be this. The average velocity between this point and this point would be the slope of the secant line, okay? And that's what this is. This is y2 minus y1 over x2 minus x1. It's the change in y over the change in x. All right, it's pretty straightforward here. Instantaneous velocity then is just like how we applied limits to the average rate. We're applying limits to the average velocity, okay? And so we end up with the instantaneous velocity being the derivative of the displacement function, or it could also be expressed as the limit of the slope of the secant line. Okay, so the limit of the average velocity. okay? And we've seen this expression before. So that's velocity, that's the rate of change of the displacement, okay? Velocity is how fast the displacement is changing, okay? I guess you could say how fast s of t is changing, okay? And again, you do need to know that velocity is a vector quantity as well. Okay, it's a vector quantity, so there could be a direction. I could end up with the velocity function being a negative number, and or the velocity being negative, and so that means it's moving in a certain direction. Okay. Likewise, acceleration. When we talk about acceleration, the average acceleration is the slope. If I have a velocity function, it's the slope of the secant line between 2 points that I'm interested in. Okay, so let's say if this was time 1 and this was time 2, well, the slope of the secant line would then be the average acceleration of the body of the point P. Okay, so the acceleration is really how fast. Okay, it's how fast v of t is changing. How fast is the velocity changing? Okay, that's really what it is. And again, this is also a vector quantity. Okay, so the sign matters when we talk about acceleration in this context. So just like we did with the previous, when we went from s of t to v of t, when we go from v of t to a of t, the average acceleration is the change in velocity over the change in time. Okay, so that's average acceleration. When we talk about instantaneous acceleration, it's again the same thing. We're applying the limit to the average of acceleration, and we end up with a of t equals v prime of t, which is the limit as the average acceleration becomes closer to the instantaneous acceleration. All right? Okay, so units, when we talk about the displacement, velocity, and acceleration, our units are usually going to be in whatever my displacement units are, which could be meters or kilometers or whatever. My velocity will be in meters per second or distance units per second, or whatever my time units are. And my acceleration will be in meters per second, or distance per time unit. Okay? And we have two different notations here. This is the same, these are the same, and these are the same. Right? So just to recap, checkpoint, this is a checkpoint. S of t is displacement, and we represent that with s of t. S is a function of time. Okay? And for these kinematics problems, we'll mostly be looking at my independent variable being time. Okay? And velocity is the derivative of my displacement, and my acceleration, instantaneous velocity here, instantaneous acceleration is the second derivative of my displacement, or the derivative of my velocity. All right? And initial conditions are was one of our key words that we talked about at the beginning. Well, that's just saying what is my, it's usually information that's given to me, but it's whatever my conditions were at time equals 0. So s of 0 could be, for instance, 1. Okay, that would be an initial condition. My velocity, right when I start timing, right at the very beginning of my problem, my velocity could be -4. Okay, meters per second, something like that. Okay, so these are called initial conditions, and they will be used in different scenarios. All right, so just remember that we will only be considering motion when we do these types of problems on a straight line. Okay, it's either going to be horizontal or vertical. So when we do these kinematics problems, we'll only be talking about straight line motion. All right? Let's do one example. Okay, a particle moves in a straight line with a displacement from O, or 0, O, given by this function. Okay, so this is the displacement function. S of t is 3t minus t squared, and it's given in meters at time t seconds. So my independent variable is t, or time, in seconds, and my dependent variable is displacement in meters. Okay, what is the average velocity between time 2 and time 2 seconds and time at 5 seconds? What's the average velocity between these 2 points, or between the point time is 2 and the point time is 2 plus h? Okay, and then what is the limit of this expression, and what does it mean? All right, so let's think about what that means. All right, A is fairly straightforward, right? Average velocity, we said, was change in distance or displacement over change in time. Okay, we know this from science. So on the bottom, I have right away, I have probably 5 minus 2. Okay, on the top, we're going to have s of 5 minus s of 2. Okay, so I need to find out what s of 5 is and what s of 2 is. Well, what's s of 5 and what's s of 2? Okay, if I plug in a 5 in here, I have 3 times 5 minus 5 squared. Okay, so this is going to be a negative number, right? So that's going to be negative 10. All right, 15 minus 25 is negative 10. S of 2 would be 3 times 2 minus 2 squared. So that'd be 6 minus 4, so that'd be 2. All right, so if I take the difference of these, let's plug that back in. If I put minus 10 minus 2 all over 5 minus 2, I end up with minus 12 over 3, which is minus 4. Okay, so minus 4 is my velocity. Notice that there's a minus sign. Okay, so it's in minus 4 meters per second. That would be my average velocity. So what is that telling me? Okay, it's saying I'm actually moving not in a forward direction. Okay, if this was my movement, okay, let's say I was going, let's say this here is 0, and I was going this way, and that's positive. Well, if I'm starting way at negative 10 and I'm going to point 2, my velocity is actually going to be, my average velocity is going to be a negative 4. Okay, so that means I'm actually, the average velocity would mean I'm going slightly backwards. Okay? All right, let's look at the average velocity between these two other points. Okay, so what's my average velocity for s of 2 plus h minus s of 2 all over 2 plus h minus 2, right? Well, if I expand this out, okay, let's go ahead and find s of 2 plus h. I'm just going to substitute that right in, okay? What was my s? My s was 3t minus t squared, right? So if I plug that in, I have 3 times 2 plus h minus 2 plus h squared minus s of 2, which we found to be 2, okay, all over 2 plus h minus 2 will just give me an h on the bottom, okay? If I expand this top part out, I get 6 plus 3h, and then I get minus 4 plus 2h plus, sorry, 4 plus 4h plus h squared, right? So that'd be minus 4 minus 4h minus h squared minus 2 all over h. And that will simplify to, okay, if I simplify that, I end up with minus h squared all over h. I can factor out an h there. Okay, if I factor out the h's, okay, the h's will cancel here. I end up with a minus 1 minus h. So my average velocity here would be minus 1 minus h. Okay, sorry, that would be a plus and that would be a minus still. Okay, so it would be 1 minus 1 minus h meters per second. All right, that would be my average velocity in terms of h. All right, now let's find the limit of this. What's the limit of this? Okay, so the limit as h approaches 0 of this expression is really just the same as this expression, isn't it? Okay, what's minus 1 minus h? The limit of this, well, if I can just solve this limit by substituting, and I end up with negative 1. Okay, by plugging 0 in here, I end up with minus 1 meters per second. Okay, what does this mean? What does this mean? Okay, you can see that my f of x here, or my s of 2, is my starting point. So what this tells me is this is the instantaneous velocity, right? Instantaneous velocity of the particle p, right? Of my particle when at this time, okay? At time is 2. Okay? So up here, this was my average velocity. You can see how off this was because it had a big interval. It had a 3-second interval, whereas this has an instantaneous velocity. There is no interval. I'm looking at right at a point. Okay? So you can see how different this is from this. All right.